So last time we were in section 3.3 and we just finished talking about the second derivative test for local extrema and concavity. And so the next topic that comes up in section 3.4 is curve sketching. There's nothing new in section 3.4. We want to use all of these techniques we've learned for analyzing the function, the first derivative and the second derivative, to put all that information together to sketch a curve. So we'll sort of start that here with this problem. So here, it's a find the local max local min problem of this polynomial function f of x equal to negative x to the fourth plus 6x squared minus 4. So the first step here is that we want to find the critical points. So basically, finding local extrema is about finding critical points and classifying them. So I take the derivative. Here we get that the derivative is minus 4x cubed plus 12x. And so I'm going to factor out the common term, which is a minus 4x, set it equal to 0. And so this part I want you to, is important. So here, 4x is 0 when x equals 0. So that's easy. This is the part I want you to pay attention to. X squared minus 3 will be 0 when x squared equals 3, or when x equals the square root of 3, plus minus 3. So here we have 3 critical points. The domain of the original function f of x is all reals because it's a polynomial. So these are critical points. And so now we need to classify them. And so that's something to always keep in mind, that once we find critical points, we then need to classify the critical points. And we now have 2 ways of doing this, either using the first derivative test or the second derivative test. As I said before, in some situations, if it's easy to use the first derivative test, then that might be more useful, where it's complicated to find the second derivative. However, in other situations where it's easy to find the second derivative test, that might be an easier way to go. It might be more efficient. So here, certainly, it's easy to take the derivative of this polynomial to find the second derivative here. So the derivative of, and I'm taking the derivative of the non-simplified form. If I do this factored version, then I'm doing a product rule and it's unnecessarily complicated. So the derivative of minus 4x cubed plus 12x is minus 4 times 3x squared plus 12x, or minus 12x squared plus 12x. And again here, I'm going to factor out the common term, which is a negative 12, set it equal to 0. So here, I'm doing the second derivative test. I don't want to set it equal to 0. If I was looking for inflection points, then I'd set it equal to 0. So I'll do that in a second. So here we're doing the second derivative test to classify the critical points. So now let me plug in these critical points, 0 plus minus root 3, I need to plug into the second derivative here. And if the second derivative is positive, then it's concave up. And if it's concave up, we have a local min. And if the second derivative is negative, then it's concave down and we have a local max. So here when I plug in 0 for x, we can see we get negative 12 times negative 1. We get 12. 12 is positive. So let's think this all the way through now. So if it's positive, that means the function is concave up. And so here at the bottom, we have a local min. And so we have a local min. And for the other critical points, plus minus 3, I plug plus minus 3 into the second derivative here. And I did them both at the same time because you get the same answer. If you take plus or minus 3 and square it, it becomes 3. 3 minus 1 is 2 times 12 is negative 24, because I have a negative 12 outside. Negative 12 times 2 is negative 24. So it's negative, so that means it's concave down. If it's concave down, our point's right here at the top. So we have a local max. And when you can find the second derivative, to me, that's a lot nicer than plugging in and checking the SIGN, the way we do the first derivative test. But it all depends on the function. So we can conclude that we have the local min at x equal to 0, local max at x equal to plus minus 3. The other thing we can use the second derivative for is concavity information and inflection points. So now we're sort of starting all over again. It's a similar procedure where we figure out where the second derivative is 0 or undefined, and then we classify those points using a sign chart. We're basically finding the critical points of the first derivative when we figure out where the second derivative is 0 or undefined. So here I'm setting -12 times x squared minus 1, I'm setting this equal to 0 to figure out where the second derivative is 0. It doesn't have a denominator, so it's not undefined anywhere. And so we can see that it's 0 at plus minus 1. And now I just need to classify this. And so what does that mean? We're going to just do basically check the SIGN of the second derivative. I'm basically going to do a sign chart for the second derivative. So here I'm going to be looking at f double prime. And on my axis here, I'm going to put down the two potential inflection points. I'm going to put down -1 and 1. And now I have to check. So here's -1 and here's 1. So now what are we checking? We're checking the SIGN, the sign of the second derivative. So I'm looking at this function. So for example, here if I pick, I guess -2, plug it in, -2 squared is 4, minus 1 is 3 times -12. So here it's going to be negative right here. So to the left of -1, this is going to be negative. That's going to be concave down. Between -1 and 1, of course, pick 0, our favorite. Plug 0 in, -12 times -1, this is positive. So it's concave up. So we have inflection point and -1. And then to the right of 1, for example, pick 2. Oh, it's negative again, concave down. And so you see the change in concavity means we have inflection points at -1 and 1. And for inflection points, you know, I've given here the X and Y coordinate because typically that's what you want if you're graphing it. So I also want to contrast this example. So yeah, this is how we found local extrema, but then I also want you to think about, okay, what are the absolute extrema of this function? So here, this is the same function, but now I want us to think about absolute extrema. Here we don't use the shape. Remember how we find absolute extrema. We're going to find the critical points and then find the value of the function, the y value of the function at the critical points and at the endpoints of what? The domain. Here the domain is -infinity to infinity. So for checking the endpoints, we're going to do a limit here. So from the previous slide, we saw the critical points are 0 and plus minus √3, and our endpoints are -infinity and infinity. Now I need to check the value of the function at these points. So I'm checking the value of the function. So I'm plugging in the critical points into the function. So f of 0, you plug in 0, you get -4. F of plus or minus √3, when you plug it into the x to the 4th, √3 squared is 3, and then you square that, you get 9. And it's going to be positive because it's the 4th, and then there's a minus symbol in front of it. So -9 to the 4th. Here, x squared will just be 3, so 6 times 3, and then -4. So we get f of plus minus 3 is 5. So I've checked the critical points. I now need to check the endpoints. Quote unquote endpoints. Here, the endpoints are infinite. And so we have to use limits. So here, you have to, math builds on itself. So we can't forget what we've learned before. Here it's a limit. The first thing I'm going to try and do is apply the limit. When you put an infinity, this becomes -infinity. This is infinity. So we get an infinity minus infinity type indeterminate form. And here the trick is to factor out the highest order term. I factor out an x to the 4th. We see that these two terms, 6 over x squared and 6 over x to the 4th, those go to 0. X to the 4th goes to plus infinity, but it's multiplied by a minus sign. So this limit is -infinity. So if the limits of this function is negative infinity, there's no absolute min. This says as the function, the right tail of the function goes down forever. So there's no smallest value in the range. There's no absolute min. And I need to also take the limit as x goes to negative infinity to check the other endpoint, right? Our endpoints are quote unquote endpoints are minus infinity and infinity. So if you take the limit for the other endpoint, you can factor out x to the fourth. It's this, you get the same answer because x to the fourth is always go to plus infinity times minus one. So the limit again is minus infinity. So there's no absolute min. And now if I look at these numbers, I see that 5 is the largest. So there's going to be an absolute max value of 5, which is occurring at 2 points, plus x equal to plus and minus root 3. And there's no absolute minimum for this function. And so it really helps to see what the graph looks like. And you should think about the concavity chart from the previous slide here. It's concave down, concave up, concave down. We use the concavity, we plot the points, and you can get that the graph looks like this. And here's the absolute max. Here's a local min, and you can see there's no absolute min because the function will go down to negative infinity forever. And this point right here is the inflection point. You can see where it goes from, concave down in this section, and then at the inflection point, concave up, and then at the inflection point, concave down. So we now want to kind of practice this procedure of doing what's called synthesis. So we're taking all of these different pieces of information from the function, the first derivative, the second derivative, and we now want to synthesize all these things to create one picture that has all those properties. Remember, this section 3.3, section 3.4, local extrema curve sketching will not be on the test this Wednesday. This material will be on the test in April, which is exam 3, which we don't need to talk about right now. But this will be a good review. Okay, so the one nice thing about today's material is it's a good review of all the material, and that never hurts. It always helps to keep going and reviewing over these facts. That's how it really gets in the brain. So for given a function f of x, to sketch the graph, from the original function f of x, we can find domain, range, x and y intercept information, horizontal and the vertical asymptotes, and symmetry information, if any. From the first derivative, we can find the critical points, including getting information about whether you have a horizontal or vertical tangent, increasing, decreasing behavior, and local extrema, again, if any. Now, if the function we're trying to graph is over a closed interval, then we should all, look for the absolute extrema. So here then, if it's a closed interval, typically we just want to do closed interval method and find the absolute extrema. From the second derivative, we can find concavity and the inflection points. And then we take all of this information and put it together, as well as using the curve shape guide. So here I've made a little diagram that tells me what the shape of the function looks like if, for example, it's concave up and increasing, or if it's concave up and decreasing, so here I've kind of cataloged the general shape of the function. If it's concave down and increasing, or if it's concave down and decreasing, or if it's concave down and increasing. The actual curve might be way more have a lot of curvature, or be kind of stretched out a little bit. That we don't know. That we'd kind of have to take from a case-by-case basis and from plugging in a few points. So let me show you an example. So with these graphing problems, the student is typically given the function, the first derivative, and the second derivative. Probably in the homework, you'll have to calculate those, but it's good practice for you. So here we want to graph the function x over x squared minus 1, this function here, f of x, that's been given to us. And so we're also told the derivative and the second derivative. So we'll use that in a second. Let's just focus on f of x and get all the information we can from f of x. So for the domain, remember the way you figure out the domain is you ask about function restrictions. Here, we should notice it has a denominator, and the denominator can never be 0. So here the restriction is x squared minus 1 can't equal 0, or when you solve that, x cannot equal plus or minus 1. So numbers that make the denominator 0 but not the numerator 0 are going to be vertical asymptotes. So this will also be where we will check for asymptotes in a second here. For x and y intercepts, for the x-intercept, you let the function equal 0 and solve for x. Here, when I let the function equal 0, the function's a fraction. Remember, a fraction will equal 0 when the numerator is 0. So we get the x-intercept is 0, 0. And to find the y-intercept, just plug in x equal to 0 for your function. So here we get that the y-intercept and the x-intercept are the same. This function only goes through the x and y axis at one point at the origin. For horizontal asymptotes, remember we take the limit as x goes to infinity and as x goes to negative infinity. And here, you can use dominance of powers to answer the question. I did it both ways. I used the actual technique where you factor out the highest order term, but you don't need to at all. I would just do dominance of powers. So for example, for this second fraction here, I would ignore the minus 1. Whoops, let me make that so it disappeared. Yeah, I would ignore the minus 1. You're looking at x over x squared. And so now do algebra, cancel the x, cancel one of the x's in the denominator. As x goes to negative infinity, 1 over x, this is 1 over x. As x blows up to infinity, this limit will be 0. Anyway, both limits are 0 by dominance of powers, so the conclusion is the x-axis, y equal to 0, is a horizontal asymptote. So the tails of our function, as x goes to the right or to the left, the tails of our function will approach the x-axis. For vertical asymptotes, this is connected to the domain. This goes back to the domain. Here, the function's undefined at plus minus 1. I need to check x equal to plus minus 1 with a limit. And here, when I try to take the limit, we have to remember all our technique, right? It's a limit, so let me plug it in. When I plug it in, I get 1 over 0. And I have to be careful. I can't conclude this is plus or minus infinity. A number over 0 will be plus or minus infinity in a one-sided limit. Here, this is a two-sided limit. So yeah, I have to check the limit approaching 1 from the right separately from the limit approaching 1 from the left. Here, when you plug it in, you get a number over 0. And you can show, for example, when x approaches 1 from the right, x will be positive, x plus 1 will be positive, x minus 1 will also be positive if we're approaching 1 from the right with numbers larger than 1. So here, number over 0 and the function is positive gives us a plus infinity. The other one is minus infinity because, again, this x minus 1 term will be negative if you approach 1 from the left. At any rate, one or the other limit imply we have a vertical asymptote at x equal to 1. I still wanted to do both limits so I know how the function behaves. So I know that when we're approaching 1 from the right, the function will go up. And when we're approaching 1 from the left, the function will go down to negative infinity. So these limits, even though I just needed one of them to confirm that it's a vertical asymptote, both of them give me information about the function behavior. So similarly, I do the limit as x goes to negative 1. You look at the one-sided limits and you can, get that they are undefined, they blow up. And so we have a vertical asymptote at x equal to negative 1. So now I want to get the information from the first derivative and the second derivative. Okay, but before I do that, one last thing I do with the original function is make a sign chart. So the sign chart here, this is for the original function f of x. It's an x-axis. Put down all the x-intercepts and vertical asymptotes, anything that crosses the x-axis. So vertical asymptotes cross the x-axis and x-intercepts. And then I'm checking the SIGN of the function by plugging in points. For example, let me pick negative 2 here to the left of minus 1. Plug it into the function. I get negative 2 over 4 minus 1. I get negative 2/3. So the function is negative. And in that way, I can figure out, make sure it's clear what we're finding out. Here, the function is below the x-axis. So here, the pluses and minuses tell me if the original function f of x is above or below the x-axis. So between -1 and 0, our function is positive. Between 0 and 1, it's below the x-axis. And to the right of 1, it's above the x-axis. I'll show you how we use all this information in 1 second here. So now I look at the first derivative. I need to find out where the first derivative is either 0 or undefined. So I'm finding the critical points, and then put that on a number line and classify those critical points. Check if they're local max or local min. In this case, x squared plus 1 is always positive because x squared is always greater than or equal to 0 plus 1. X squared minus 1 quantity squared is also always non-negative. And then there's a minus sign in front. So here, this derivative is always negative. It's not 0 anywhere. Here, the numerator is never 0. For the numerator to be 0, x squared would have to equal -1. And that's never going to happen because we're over real numbers. So there's no numbers that make the derivative 0. The derivative is undefined at plus or minus 1, but those are not critical points. We determined plus and minus 1 are actually vertical asymptotes. So here's what the number line looks like for my first derivative. I've got anything that crosses the x-axis on there and any critical points, where it's 0 or undefined, but we don't have any. So I've got the vertical asymptotes and I'm checking the SIGN. Here it's always negative as we saw. In this case, when it's negative, that means the function is decreasing. So that's why I've got this downward pointing arrow. Here, this is the first derivative, so it tells us about increasing, decreasing behavior. Finally here, for the second derivative, I take the second derivative. Again, I want to know where is the second derivative 0, where is it undefined? X squared plus 3 is never equal to 0. The only way x squared plus 3 can equal 0 is if x squared equals -3, and we're only restricted to real numbers, so x squared will never equal -3. So the only way this can be 0 in the numerator is if x is 0, if the 2x is 0 or x is 0. The denominator here is undefined at plus minus 1, but we know those are vertical asymptotes. I'm going to put the vertical asymptotes on the x-axis here because it's possible for concavity to change around the vertical asymptote. It's possible for the increasing, decreasing behavior to change around the vertical asymptote. It's possible for a function to go from positive to negative or negative to positive as you go across a vertical asymptote. So that's why, I'm putting the vertical asymptote here in all of these number lines. And the number that made the second derivative 0, which was 0. And then I'm checking the SIGN. So be careful, I'm plugging into the second derivative here. And I'll let you check, but I was able to figure out that, it's negative to the left of -1, it's positive between -1 and 0, negative between 0 and 1, and positive to the right of 1. Here, the positive and negative indicate the concavity, whether it's concave down or concave up. And here we can see specifically around 0, the concavity is changing from concave up to concave down. So at 0, we have an inflection point. The vertical asymptote is a vertical asymptote. Even though the concavity changes around the vertical asymptote, it's not an inflection point, right? It's an asymptote. Okay, let me show you how we put all this stuff together now. So the first thing I like to do is draw the axis and put in the asymptotes and the intercepts. So I got my asymptote at -1 and 1, and my intercept at the origin. Okay, let me show you how to use this thing now. So here, if you look at this section, we're putting it all 3 together. So what are we putting together? Let me tell you. So I know the function will be below the x-axis, and then I know that it's decreasing and concave down. I can use these two to get the shape. Decreasing And concave down looks like this. So below the x-axis, decreasing and concave down on the left of -1. That's what the graph looks like right there, based on the shape guide and the fact that it's negative. And we keep going in this way. So now I look at the next section. So now I look at this section. So now looking at this part here. So this is the section from -1 to 0. Oh, I lost my graph here. Oops, sorry. Let me put this piece back in. And now if you look, this is between -1 and 0. It's positive, it's decreasing, and it's concave up. Concave up and decreasing looks like this. So look, between -1 and 0, it's positive, decreasing, concave up, and it goes through the x-intercept. If you check our limits approaching -1, this also satisfies our limits approaching -1. So now look, I move on to the next section. What's the next section? Right here. Between 0 and 1. So look, between 0 and 1, it's negative. It's below the x-axis. It's decreasing, but now concave down. Decreasing, concave down, looks like this. And so right here, look, negative, decreasing, concave down. And if you check the limit, you know, as x approaches 1 from the left, it was going to negative infinity. This is matching that. And here's that final section. I'm going to do the synthesizing from -1 onward. Again, you can see it's positive, so it's above the x-axis. It's decreasing and concave up. What does decreasing and concave up looks like this? So here, above the x-axis, decreasing, concave up. Boom, there's a graph. And so here, let me show you, I also did a computer plot. Here's what the computer plot looks like. So the black curve that's printed on your slide, that's not a sketch, that's an actual plot by the computer. And you compare it to the human sketch, that's pretty good for a human. I didn't even plot any points. Human, no plotted points, and still got good, good sketch. So that's what the synthesis aspect of it involves, and that's how I use the shape guide in combining the increasing, decreasing behavior with the concavity, and then the actual sign chart. Where is it above or below the axis? And then you can get a pretty decent curve sketch. And that's kind of the whole name of the game for sketching curves. For me, if I have these number lines and maybe, the graph of the function, or even, the equation for the function, or maybe even not. If I have these number lines, I can already sketch a pretty good, graph of the curve. And that's all this section is, where we practice doing this. So let me do 1 or 2 more examples and see how you're doing. So here we want to graph this function. If you look at each example, the type of function is slightly different. The first function was a rational function. This function involves roots, this x to the 2/3. And I just kind of wanted to do something like this just to show you the algebra and stuff. So yeah, starting out with the original function, we ask about the domain. Here, there's no restrictions on f of x. There's no denominator. We're not taking the even root of anything. We're taking an odd root. There's no restriction there. Intercepts. So for intercepts, you should notice there's a common term. So I factored out the lowest power of the common term. And so x to the 2/3 will be equal to 0 if x equals 0. And here, 2x to the 1/3 minus 3 will equal to 0. So you move the 3 to the other side, becomes positive, divided by 2, 3/2, and then you cube it, 3/2 cubed. So our intercepts, x-intercepts are x equal to 0 and x equal to 27/8. And then the y-intercept is just the origin. I checked the horizontal asymptotes. Here, as I said to review, when you take the limit as x goes to infinity, here I get it infinity minus infinity. So again, our algebra vision should notice there's a common term of x, and I factor out the lowest power of the common term. And then you can see for this product, As x goes to infinity, x to the 2/3, which is always squared, will go to plus infinity. X to the 1/3 will go to also plus infinity. So here plus infinity times plus infinity gives us plus infinity. So we know going to the right, the graph will shoot up forever. And I'll show you the graph in 1 second. We'll synthesize everything. And here, similarly, for x going to negative infinity, we again factor out the common term. X to the 2/3 goes to plus infinity. X to the 1/3 goes to negative infinity. So here I have negative infinity times positive infinity. So the limit's negative infinity. There are no horizontal asymptotes. The vertical asymptotes, there are no vertical asymptotes, since the domain of the function is minus infinity to infinity. It's important that you make this connection between the domain and vertical asymptotes. So here's a well-defined function, so no vertical asymptotes. So now let me do the sign chart for the function f of x. So for the original function f of x, I'm plugging in values like -1, like 1, and then a number to the right of 27/8, So I get the sign chart like this. So I know it's below the x-axis, between, from negative infinity to 27/8, and then it's above the x-axis. I'll show you when we synthesize how we put it all together. For the local extrema, I'm now focusing on the first derivative. And here, just an algebra comment, I want to know where the derivative is 0. For me, I notice x to the minus 1/3 is a fraction. So I write it as a fraction, and then I combine the fractions. And now I can tell where it's 0 just by asking myself, when is the numerator 0? And here, the numerator is 0 when x is equal to 1. And then I ask myself, when is the denominator 0? And here, the denominator is 0 when x equals 0. And these are both points that are in the domain. The domain of a function here is all real, so these are critical points. And so I need to classify them. And so I make, draw an x-axis with the derivative and put the critical points that we just found on there, x equal to 1 and x equal to 0. These critical points are what's showing up here on the first derivative test number line here. And then check values. I'm picking, for example, -1, plugging it into the derivative, plugging it into this function here. If you plug in a -1, I get 2 times 1 minus 1 over -1, or 2 times 2 or 4. So it's positive. So it's increasing there. And you can check I got it's positive, increasing, decreasing. And so here, if you look at the shape, I see that I've got a little hill here. So at 0, I've got a local max. And here at 1, if you look at the shape, it's decreasing and then increasing. So at 1, we have a local min. And of course, I want the x and y coordinate because I'm going to plot it in the graph here in a second. Finally, I'm looking at the second derivative. If you look at the second derivative, the numerator is never 0. So the second derivative is never 0 anywhere. The denominator is 0 at 0. So technically speaking, the second derivative is undefined at 0. So I put 0 on my number line for the second derivative. And now I need to check if 0 is an inflection point. I need to check, does the SIGN, the sign of the second derivative, change around 0? Here the answer is no. Because x is always raised to the 4th power, it's always going to be non-negative. So here it's always non-negative. So it's concave up before 0 and concave up after 0. I don't have a concavity change, so there's no inflection point at 0. But we have some information for the graph. So let's put it all together. So first, I want to plot my intercepts, and the local max and local min, and plot all those points in. So this is my x-intercept. It's also a local max. And here's the local min. The y value I calculated was -1, the local min value. And here's the other x-intercept. Now we're doing the shape analysis. So now I'm looking at this section and I'm saying, aha, okay, it's negative, it's increasing, it's concave up. So I'm looking for increasing and concave up looks like this. And it's negative. So I'm going to start down here, increasing concave up to 0. And so now let me look at the next section. From, I guess, 0 to -1. Whoops. From 0 to -1, I'm looking at this section. So you can see it's from 0 to -1. It's still negative from 0 to -1. It's decreasing. That makes sense. It's decreasing. And it's concave up. So decreasing, concave up. So here it goes like this. That's that decreasing concave up. And you can see now this final section here. Well, not final section, I guess. Second to the last section here. From -1 to 27/8. It's still negative. It started increasing though. And concave up. Increasing concave up looks like this. So here, increasing concave up to the x-intercept. And now if you look at this final section, it's the final piece here from 27/8 onward. Look, it's positive, increasing, concave up. So that's going to look like positive, increasing, concave up is going to look like that. And so we can check the computer plot looks like that, which is really good. I mean, I didn't plot a single point. I mean, other than the x-intercepts and the local extrema. This is using the shape analysis and those key points. If I wanted to plot a couple of points, I'd get, a really close graph. So this is a great curve sketch right here. It's got all the, features, behaviors, and all the pieces we're looking for. And this is what I'm talking about, the synthesis aspect of doing curve sketching, where we're combining all of this information from the first derivative, second derivative, function, the original function, the first derivative, second derivative, and putting it all together. So let me do one more example here, and we'll see how you're doing. So this function, as I said, they're all slightly different. This function is just a very nice, well-behaved polynomial. So here, since it's a polynomial, from the original function, we get the domain is all reals. So I know there's going to be no vertical asymptotes. The intercepts here, this is about algebra. I notice x cubed is a common term. So I'm factoring out x cubed and setting that thing equal to 0. And so we get our intercepts are -2 and 0. And for my y-intercept, I get that f of 0 equals 0. So here, checking for horizontal asymptotes, x to the 4th, as x goes to infinity, goes to plus infinity, x cubed, that goes to plus infinity. The limit going to the right is plus infinity. The limit going to the left, x to the 4th is plus infinity. 2x cubed, that'll go to negative infinity. So this does give me an indeterminate form, but that's okay. We know what to do with indeterminate forms here. Factor out the common term. Our algebra vision is really important, that when we see x to the 4th plus 2x cubed, there's a common term there that we recognize. X cubed goes to negative infinity. X plus 2 goes to negative infinity. Negative infinity times negative infinity is plus infinity. So in both cases, we see there's no horizontal asymptotes. But we know the tails of the function on both sides go up forever as x goes out. As I said, there's no vertical asymptotes because of the domain. And here's what the sign chart looks like for the original function f of x that tells me where the function is above or below the x-axis. And for the first derivative, it's easy. Here you take the derivative, you get another nice polynomial. Again, basic algebra, I factor out the common term, set it equal to 0. I get 2 critical points, -3/2 and 0. And those are the points I put on my number line for the first derivative. So I'm doing basically a first derivative test here. When I check the signs, and you can check the signs, I got negative, positive, positive. So if you do the shape analysis, we can see clearly there's a min here. There's nothing at 0. It's increasing and then increasing. So there's not a local min or max there, but there's a min at -3/2. Finally, the second derivative, you get 12x squared plus 12x. Again, I factor out the common term, set it equal to 0. I get 2 places where the second derivative is 0. Obviously, for all of these functions, they're not undefined anywhere because there's no denominator. And so for my second derivative now, on the number line, I put down these numbers where the second derivative is 0. Again, check the SIGN of the second derivative. And I get this pattern where it's plus, minus, plus. And remember now, the pluses and minuses mean concave up, concave down. So concavity changes around -1. So there's an inflection point there. And concavity changes around 0. So there's also an inflection point at 0. So here I've summarized everything here. Here are my 3 number lines with my handy shape guide. Right? So the first step I like to do is plot the x-intercepts here. So these x-intercepts I plotted on the graph you can see right here. There's -2 and 0. And then I plotted, there's this local min here at -3/2. Here's a local min. And my inflection points at -1 and 0. There's the inflection points at -1 and 0. So now we just want to fill in the shape in between, So here, up to -2. Look, it's positive, then decreasing, but concave up. Actually, if you look, it's actually positive, then it's negative, but it's concave up and decreasing up to 3/2. So here, up to 3/2 here. Let's see if I can get right there. You can see what happens. It's positive, decreasing concave up. Okay, so decreasing concave up looks like this. The only difference is it's concave up and decreasing the whole time, except that it goes from being positive to negative. So here, I'm going to do a long line here, coming down. It's concave up, decreasing, goes through 2, hits this min. I know it's terrible, but you get the idea. And then here, look. Once we get, so I'm doing -3/2 to -1 now. Okay, so look, it's negative below the x-axis, that makes sense, but now it's increasing. Increasing and still concave up. So it's gonna look like this. So here, increasing concave up. And then concavity changes because I have an inflection point. So now from -1 to 0, it's still negative, it's increasing, but now it's concave down. Increasing and concave down looks like this. So here I need a piece that's increasing concave down that hits 0, which is the x-intercept. Last final section here, from 0 onward. So look, it's positive, it's above the x-axis, it's increasing concave up. Increasing concave up looks like this. So here I'm going to go above the x-axis, increasing concave up. So that's my sketch. Here's what the computer plot put that section in. Okay, I was slightly off, but it still looks pretty good. There's this section. Okay, I could do a little more curvature, but I mean, I'm trying to draw it on this trackpad. Boom, that looks great. Bang, oh yeah. Oh yeah, all the way home. Okay, I could have plotted some points, but that looks great. That's a beautiful curve sketch right there, y'all. Feeling it, looks good. So that's this whole procedure with synthesis. The next topic is slant asymptotes, but I don't want to start that yet. We already talked about a lot, and so this is a good place to stop.